Every day, the future's getting closer.
Welcome to Master the NEC, where we talk about the National Electrical Code and all things electrically related. My name is Paul Abernathy, your host, and welcome to today's podcast. Well, hello, everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code, all things electrically related. My name is Paul Abernathy, your host as always, and welcome to the podcast. So today's episode is going to be one where you're going to have to possibly listen and then stop and maybe write some stuff down, come back and listen a little more to get a full understanding of what we're going to talk about in today's topic. Because today we're going to talk voltage drop. We're going to talk formulas, concepts, conductor properties, all the good stuff you've ever wanted to know, or maybe more than you care to know, about voltage drop. We're going to talk about where the code talks about mandatory requirements for voltage drop. And of course, we're going to talk where it's just optional, good design information, and things like that. So we're going to cover all those things in today's topic. So hopefully you can stay with us, and it'll be a pretty good podcast for you to listen to. And I'm going to try to paint a mental picture of all of these formulas so that at some point you'll take out a piece of paper, you'll write a line down the middle of the paper. On the left side it'll be single phase, on the right side it'll be three phase, and that way you have these formulas that maybe later you can put in your code book, maybe in the front of the code book where you have the blank spaces where you have us code panel members are at, and you can just simply utilize that space to put formulas in. Remember, again, making sure that your state in your exam administrative bulletin for whatever state you're in allows for you to mark in your code book. If it doesn't allow you to mark in your code book, then just write these down on a piece of paper. That way you can look at them and learn these different formulas. But in many states, you can actually write in your code book and highlight it and do different things. But again, you need to check with your state. Don't assume all states allow that, and don't tell anybody Paul said you could. Again, every state is different, so you have to check with your own state. Okay? All right. So first things first, let's talk about conductors and the property of conductors, because that's real important that we cover the basics of the conductor itself. And when we're dealing with voltage drop, a couple things to remember: that when we're talking voltage drop, it's designed from the source to wherever the load is. At the end of that load, wherever you're at the load, what is the voltage at that point? Now, all types of equipment operate in different voltage ranges. Motors most frequently will give you a value on the motor's nameplate that'll say it operates between this range of voltages, and any operation below that or above that could potentially harm the motor. It could cause it to be inefficient and burn up, bearings wear out, all kinds of things could happen. So while the National Electrical Code only mandates voltage drop in two simple areas, generally it is optional. It's just a good recommendation. Okay. Now, most of the energy codes now are kicking into some type of the IECC, which is requiring some type of voltage drop to be considered when you're designing a building. But in most cases, the everyday electrician is not aware of that. If you're doing a job and you're not aware of a voltage drop, and you know that it's not a mandate of the NEC, but you know that it's in informational notes, which aren't mandatory rules, but it's just good information. Many people say, why isn't voltage drop in the National Electrical Code? But they say it's not because it's not a safety concern, and the NEC deals with safety. And that's more design, and that's not really the place for it in the NEC, although I'd argue that the NEC is moving in a design direction, even though they like to say it is not. We can beg to differ on some of those things. When anything that makes me do something, it's a design, even though it is a minimum safety standard, but I digress. I'll get off that soapbox. All right, so at the end of the day, we're trying to make sure that the voltage from the source to the load is falling within an adequate range that's not going to cause equipment or motors or whatnot to run inefficient. Okay? So we're going to talk about all of that today and what the voltage drops means, so that by the time we're done in this podcast, you know everything that you'll want to know about voltage drop, or that you'll need to know about voltage drop. So let's talk conductors. Now, in the National Electrical Code, we have a table. Actually, two tables. The first one is Table 8, and then there's a Table 9. Now, these are in Chapter 9 of the NEC. They're very applicable as referenced, and you'll get a lot of tables used for raceway fill calculations, Table 4, Table 5. If you're doing compact conductors or aluminum or copper, you'll need to use Table 5A, all that good stuff. If you're dealing with bare conductors and you need to know what the DC resistance is of it, or you need to know what the circular mils of a conductor is for whatever reason, then you're going to be in Chapter 9, Table 8. If you're dealing with an AC circuit, which has this element of induction as well as skin effect, which is, again, negligible when we're dealing with 60 hertz normal building wire, so we don't usually take that into consideration. But in any case, you're going to look at Table 9. It's going to give you that value. Now, Table 9 is a specific installation type-based table. But we typically will use that anyway when we're doing any type of AC circuit calculation and we're trying to determine what the resistance is based on that. But if you're on an exam, more often than not, all of the values that they're going to ask you about when they're trying to determine how you use a formula are going to be based on DC. Now, one of the key differences between DC and AC current, or circuits, I should say, is that AC circuits do have things like skin effect and induction that takes place because actually the current travels an outside perimeter of a conductive material, and the skin effect is how deep that conductive medium penetrates based on frequency. Whereas in DC, you don't have that direct current. It really uses the core of the conductive material, so you don't have the same things that can affect it with DC as it does affects an AC circuit. Okay? Now, Chapter 9, Table 8, that table is the resistance of a conductor when it's placed in PVC, aluminum, or a steel raceway. Again, in steel raceways can create a magnetic effect. In that case, create some factors that can affect it from the induction. But skin effect, again, is usually not something in the frequencies that we use for building wiring and what you're going to see on an exam. Usually is not something that's going to have any real detrimental effect on the application. So it's, again, negligible and usually not considered by most designers. Okay. Now, when you're dealing with high-frequency systems, it can play a huge role, but that's not what we're talking about, and I am not venturing into higher frequency applications. I will never do that in my classes, okay? Somebody else can do that. I'm not into that. All right, so we're dealing with building wiring in the National Electrical Code and what we do when it falls with building wiring and things like that. Okay, let's talk about some things when it comes to conductors. Some of the things to remember is the larger the circular mil of a conductor, the smaller the resistance. So a 500 kc mil, okay, is going to have less resistance per foot than you would for a smaller conductor. Okay, it's just a given. For example, even if we're looking at per 1,000 feet, if we look at a 6 AWG copper, it's 0.491 ohms per 1,000 feet. And again, you get that from Chapter 9, Table 8. Well, a 3-aught copper for that same 1,000 feet is only 0.0766 ohms for 1,000 feet. So you see, the bigger the conductor, the lower the ohms. All right, so the smaller resistance, therefore. Okay. Obviously, that plays an effect with the larger conductors can carry more current. Okay, it kind of all starts working together, so you kind of see what's going on here. The bigger the size, the more current it can carry. Okay, so the larger the circular mils, the lower the resistant to current flow is in that conductor. So when we look at a Table 8 and we look, for example, a 6 gauge, AWG, again, AWG stands for American Wire Gauge. The old version of that was Brown and Sharp. Okay, so we use AWG. And the area in circular mils of a 6 gauge copper is, or be honest with you, 6 gauge aluminum, doesn't really matter, is 26,240. And that is the circular mils. Whereas for a 3-aught copper, or 3-aught aluminum, doesn't really matter, the circular mils is 167,800 circular mils, okay? And contains 19 strands. When it comes to the stranding, the only thing that I will remind you, if you are taking an exam for whatever reason, the only thing I remind you when it comes to stranding is that you're going to have multiple options when you're dealing with 8 gauge or 8 AWG and smaller. You're going to have a one strand or 7 strand option, okay, because it does come in solid or stranded. Remember that because the ohms per 1,000 feet are different whether you're dealing with a solid or a stranded. Now, once you get to 6 gauge and larger, then they're all stranded, okay? So it really becomes irrelevant to your values. You know it's stranded, okay? So just good information to remember. Obviously, by now you should know the abbreviation for the circular mills is KC mills. And so when we're dealing with the 250, size 250 KC mill, that's 250,000 circular mills. If it's a 500 KC mill, it's 500,000 circular mills. And again, once you start getting to 4-aught and smaller, we're actually going to give you the circular mill value. So you'd have to come to the table and find that. Okay. So once you get from 4-aught, it immediately jumps to 250. And then from 250 up, the 250 does represent the actual circular mill. Okay. The conductor's overall diameter is listed on Table 8. This diameter is the actual wire. It's not including the insulation. Okay, so when we're dealing with bare conductors inside of a raceway, then we might come here if we were dealing with the overall area, and that's what's going to give us the overall for the square inches. Okay, now when you see the diameter for the stranding, it says inch, then that's the individual conductor. Okay, that's the individual strand that we're dealing with. Okay, but then you have what's called an overall area that you're dealing with. Okay, so and then that's converts, and it's different because then that's in square inches. And for raceway fill and everything, we usually work in square inches. So just remember that if you're going to have a bare inside of a raceway, and you're going to come over here to Chapter 9, Table 8, and you're dealing with conductors overall, you're going to be in this square inch column. Okay, so usually on exams, if you can highlight your code book, I usually tell people to always highlight the square inches because that's what you're going to deal in the most, so you don't make a mistake. So I would tell them to highlight the area and then the square inches, because generally when we're doing raceway fill or anything like that, we're dealing in area. Okay, all right. So that's what we're dealing with there. Now, conductor strand counts are also on this table. For example, it says 7 strands for a 6. Again, this is the typical. Again, understand that manufacturers can do other stranding techniques and be aware of that. But for when we're doing calculations using the NEC, we can use the tables here as they're given for that specific size wire. But for example, when we're doing raceway fill, you use the tables in the NEC as well, although from manufacturers might have varying values that they could give you. For example, PV wire. You're not going to see PV wire in Chapter 9, Table 4 or 5. Most notably for conductor, it'd be Table 5. You're not going to see that in there. Now, why is that? Well, the reason that's not in there is because the manufacturers make PV with the requirements to have its insulation meet the requirements of the PV standard. And in that scenario, it's going to be even thicker. So if you want to do a proper raceway fill, you got to contact the manufacturer, and we'll give you those values, and you can plug those values in the approximate area in square inches into your calculation to do a raceway fill. Okay? So just remember that when we're dealing with Chapter 9, Table 8, we are dealing with bare conductors. So a lot of times on exams, if again you can write in your code book, up there at the top where it says Table 8, Conductor Properties, I usually tell people to write in parentheses, bare conductor. Okay? That way they don't get confused. Okay? Again, make sure you can write in your code book, because some states won't allow it. Some testing centers won't do that. Okay? Just keep that in mind. All right, so the next thing we talk about here is DC resistant values in this table. So we're in Chapter 9, Table 8, and you see on the right, it says DC resistance, it's based at 75. If the temperature's not 75, then at the bottom you see some notes under this table. And Note 2 is going to tell you how to convert or how to change the temperature, and it gives you the formula right there, so it's not complicated for you to determine what the temperature change value would be. Okay? Not a problem. That's a conversion value. But here they are. Here's what they are based on the 75 right here. Okay? Another thing to explain to people is when we're dealing with copper, you have a difference between uncoated and coated. Uncoated is what you're going to get in normal bare copper. Okay? So you're going to be in the uncoated column. The coated column would be something like tin coated, things like that. But you're in the uncoated for normal applications. Okay? And of course, you have aluminum as well here if you're doing this equation for the aluminum. All right. Now, one thing you'll notice is if I were to take you over to Table 9, that this is also kind of how this works as well, based on the sizes from 14 gauge all the way up to 1,000. Depending, you have an AC current resistance for uncoated copper, which is pretty much where you're going to be. And you can get the effective Z for the uncoated copper, depending on what your question might ask. Here's where you get the other values in ohms as well. And again, this table is ohms to neutral per 1,000 feet. Okay, and that's what your values are here on this table. Okay, so for in our case, we're going to try to stick with the application of Chapter 9, Table 8, because generally your exams are going to be revolve around these values because they just want to show that you know how to do the voltage drop calculation, and that's it. Okay, so that's where we're going to spend most of our time. All right. So here you see the 75 degree C, you see your one, and most of the time you're going to be in the uncoded, and you're probably going to be in the ohms per 1,000 feet column. So again, if I was teaching people that can highlight in their book, I usually tell them to highlight the uncoded, and I usually teach them to highlight the ohms / per 1,000 feet column. Okay, that way they don't get drawn away from anything. All right. I never tell people to highlight this entire table because that would draw your attention away from important things, and we want to make sure our attention is drawn to important things. Okay. Example, if you're using this table, you look at the uncoded, you go down to a 6 gauge on this table. Hopefully you're following along in your code book. Again, we're in the 2017 edition. If you're in the PDF, it's on page 692. If you're in the hardbound or softbound version, whatever you want to say, then you're on page 689. Okay. The 6 gauge, if you follow it out, again, this is stranded. And so uncoded, it's 0.491. That is the DC resistance per 1,000 feet. How do we convert this down to per foot? Because we're going to need to do that later because we'll need to know what the resistance is per foot. It's really just that simple. You take this 0.491, you divide it by 1,000, and that's going to equal 0.000491. And that's what it is per foot. Now, if I have 100 feet, then it's simply take that value, multiply it by 100, representing 100 feet. So then that tells me it'd be 0.0491 per 100 feet. If I have 1,500 feet, the easiest way to calculate what it is to take the per 1,000 feet, which is a 0.491 divided by 1,000, find out what it is per foot, and then multiply that by 1,500 feet, and that's what's going to give you a resistance for 1,500 feet. Okay? So in an exam, you could get a question like that where it simply wants to know what the resistance is of a 6 gauge for 1,500 feet. And your easiest thing you can do is break it down to per foot and then multiply that by the number of feet in the question, and that's going to be the easiest way to get your answer. Okay? Any other way to do that, it's going to be convoluted and it's going to really take up time. And again, we're trying to move through this exam, and time is of the essence. And the more you start losing time based on this needless math, then chances are you're going to run out of time, or you might miss a decimal point and you end up getting the question wrong because you're stressed out at an exam. And we don't want you to be stressed out. Okay? All right. Now, let's move on to some voltage drop recommendations, and let's talk a little bit more about the NEC and how we equate things and what we're working with here. Now, there's 2 locations in the NEC which are a demand of voltage drop to be considered, and then there's other places in the code where it's a recommendation, and it's usually under what we call an informational note. And you should know by now that an informational note is really great information, but it is optional. It's not a requirement. However, if you're dealing with sensitive electronic equipment in section 647.4D of Article 647, then that's going to have a voltage drop requirement in there. Where's the other location you think it's really important that a voltage drop is taken into consideration? You guessed it, a fire pump. With fire pumps under Article 695, it's important to make sure that in an event where those sprinklers go off, or you have a stack where the fire department connects in with a fire hose on a multi-story building, you want to make sure that that pump's going to run until it burns up. Again, sprinkler systems and all this fire type of systems in a building is not to preserve the building. It's to maintain a safe condition enough so that the occupants can get out of the building safely. It's about saving lives. It's not really about saving the building. Now, a consequence of a good sprinkler system might save the building. That's great. But we really don't care about the building. Okay? Anything, people can rebuild. It's the lives that are lost that what we're concerned about. So if we can put a sprinkler on and keep this fire at bay and buy time for everybody to get out of this building, that's what we're all about. Okay, that's what we're trying to achieve. So when we talk about fire pumps, it's all about the motor. And in dealing in the motor, we want to make sure that there's a voltage range on that motor, that motor operates within that voltage parameter so that we don't prematurely fail the motor. It doesn't burn up prematurely based on poor design. It has to get enough voltage necessary to operate efficiently and effectively until it's not needed anymore. Whether it fails or somebody shuts it down because the issue is over with, the fire's done with, or whatever. Okay, that's what we have to be able to think about here. So that's why it's a requirement for fire pumps. Okay, for that example. Now, anywhere else in the code, it is a good recommendation. Okay, it's the compliance with voltage drop is purely optional, except for fire pumps and sensitive electronic equipment. Okay, now, when the National Electrical Code makes these optional recommendations, like they do in 210.19a as an informational note, or in 215.2a1 for a feeder, when it makes these recommendations, it specifically says this, and here's what the code says. It says the branch circuit conductors as defined in Article 100, sized to prevent voltage drop exceeding 3%, at the furthest outlet of power, heating, and lighting loads, or combinations of such loads, and where the maximum total voltage drop on both the feeder and the branch circuit to the farthest outlet does not exceed 5%, will provide reasonable, efficient operation. Okay, now paraphrasing, of course, but that's what 210.19a and 215.2a1 are trying to say in their informational note. Really great design hints to make sure that whatever that equipment is, that it operates efficiently. Okay, we don't want heating loads, we don't want cooling loads, we don't want motors to operate outside of their safe operation parameters in their voltage range because it could prematurely cause them to fail. Now, voltage drop for these things aren't mandated in the NEC, but I will tell you that energy codes are mandating voltage drop to be considered in the IECC, International Energy Conservation Codes, and other aspects of municipality authorities. The reasoning to me is efficiency is important, otherwise we wouldn't be pushing towards more efficient buildings and their design. But there is a safety concern to me that I don't think the NEC recognizes, and I don't think anybody that's proposed this to the NEC code-making panels are taking into effect the potential hazards that come from operating equipment outside of their voltage range, whether it causes the motors to overheat or equipment to overheat that could ultimately result in bearing lockup and a motor burnout and fires that could take place. And that, to me, is a direct hazard. But to this point, nobody has done anything about it. And most of the people that are against it would say, Paul, we've been building buildings for years. They're not burning down. What's the problem? Stop your crying. And I'm sure they probably have some valid points there. And then there's others out there that would say, Paul, the only reason you want voltage drop to be mandated is because you work for a wire and cable company. That is not true. Most people that know me know that I don't work like that. I'm about what's best for the code. I'm about what's best for safety. But at the end of the day, they got a point. I do work for a wire and cable manufacturer. So at the end of the day, okay, I'm going to give you some valid points there. But between me and you, we do know that if I don't operate something efficiently and it wears out prematurely, that it does cost money. And I understand that the NEC is not money driven. I get it. However, some people will even argue that the advent of expanded use of AFCIs and all these other things are simply lining the pockets of the manufacturers that make those devices. Okay? So while I'm not going to win any friends over that statement, the reality is we do change things, and I'm a big believer in AFCIs as a safety thing, so I get it. But I'm just using some examples, okay? So wherever you lay in that argument, it could be argued that voltage drop should be a safety concern, okay? So I'm just laying that out there. Now, all that considered, let's talk about the recommended maximum voltage drop that the NEC gives you recommendations for. Now, let's look at it this way. The recommended maximum voltage drop for a combined feeder and branch circuit is 5%. However, the voltage drop for feeder is not necessarily resulting in a 2%. What I mean by that is the recommendation is that the branch circuit not exceed 3%. So by virtue of that, that means the feeder would be at 2%. But you could have a branch circuit where, let's say you have a motor and the motor is only 10 feet away from the source to the actual load, and the voltage drop on that branch circuit is only 1%. Well, if that's the case, then I can have 4% in the feeder itself. So you see how that works? So I'm not exceeding 5% overall. And I'm attempting to not exceed 3% for the branch circuit because we don't want to exceed 3% in the branch. But I could, if my percentage was lower than 3 in the branch circuit, have a bit higher allowance for voltage drop in the feeder. So you see how that works. So we're trying to not exceed 5%. Now, what you're not wanting to do is have 4% in the branch and only 1% in the feeder, because we want to steer towards the branch not exceeding 3% for the branch, 5% overall, okay? All right, now, we talk about the code in these informational notes, whether it's branch circuits or feeders, and we make these recommendations for voltage drop not to exceed a certain value, but you won't see that language when it comes to service conductors, so it doesn't have that same note in 230. But you do get that recommendation for feeders and branches. Also, remember that the conductor's voltage that is dropped is a percentage of the source voltage. So 3% of the branch circuit is a 3% drop in voltage of the source's actual voltage value. So if it's 120 volts, 3% drop in that is what we're trying to make a consideration. And so when we're doing that, the 3% voltage drop that's into this consideration is 3.6 volts for 120 or 7.2 volts for a 240 when we're dealing with single phase. You see what I'm saying? So that's the actual voltage. And then in order to equate that to what that results in a percentage, okay, then we just do a little bit of some math to be able to do that. And so that is not really complicated in order to achieve that, to do that. Okay, and we'll talk about that, and that is basically taking whatever that voltage drop value was and divide it by the 120 or the 240, and that'll give us what the percentage is. So we'll talk about that in a second when we're looking at formulas. Okay, so don't get your mind blown yet. Calm down. We're just simply talking voltage drop and giving you the whole parameters of life, if you will. And I'll probably here in a minute explain that anyway, because I think that I want to make sure I don't confuse people. All right, so let's go on and do that now. Recommended voltage drop for a branch circuit, 3% or less. We've established that. Now, let's take an example. The maximum allowable voltage drop for a 120 volt branch circuit is 3.6 volts. How do we get that? 120 times 3%, or 0.03, however you want to equate it. All right, that is 3.6. The maximum of allowance for a 240 volt branch circuit would be 240 times 3%. That's going to be 7.2 volts. So that is your VD. That is your voltage drop, okay, in volts that we're going to utilize in a lot of our formulas, okay? So you have to do that equation to find out what your actual voltage that you are dropping that equates to that 3%, okay? The higher the resistance through the conductor, again, the higher the voltage. Much more resistance, much more voltage drop that's going to take place, okay? Conductor voltage drop could result, again, in the reduction of voltage at the load, and that's what we're trying to keep from happening, all right? Now, a single-phase feeder or branch circuit, really doesn't matter here, that has a conductor, so I have a total resistance twice that of one conductor, and that's single phase, and that's why we use the 2 in our equation, and you'll see that here in the formula. We're measuring only one distance in one way, but we're going to show you that it's a twice of what one conductor would be, and we'll show you how that works out. Whereas in a 3-phase circuit, we're going to multiply the length it's only based on one conductor, and that is going to be multiplied by the square root of 3, which is 1.732. Okay, so don't worry, we're going to talk about all that, keep you from being confused, and I'm going to give you kind of an understanding of how these formulas work. Now, talking about formulas, there's going to be some values that we use in a formula, and I need you to understand these values, whether you write them down or you kind of get used to. Whether you're doing 3-phase or single-phase, these values are not going to change, okay, based on the symbolization that I give you. For example, VD. VD is the voltage dropped from a circuit, and that is the literal voltage. How do we get this? If we know it's a 3%, then we take the voltage, which is 120. Okay, we did that. We said, how do we do it? We take the voltage that's 120 and we multiply it by 3. And that's going to actually give us the actual voltage that have been dropped. Okay, so that's what the VD represents. Okay, it doesn't represent you writing in the formula at 3%. Okay, it is the actual voltage that's dropped. So you're going to have to do a little math there, okay, first off. Now, if you see the number 2 in your equation, or when would you use the number 2, that is the multiplier factor when you're dealing with single phase, because it represents the conductor going down and coming back. Okay? And so in 3-phase, you're going to substitute the 2 for the 1.732. Okay? Now, there is an equation where we're going to still use the 2 in a voltage drop calculation for 3-phase, and we'll talk about that when we get there. But I really want you to just grab the basics. So in single phase, the 2 is representing as a multiplier for the length. Now, we're only going to put in the formula the length going one way, from point A to point B. The 2 is just saying, look, that represents going down and coming back. Okay? All I'm trying to say in that formula. Okay? The next thing is the letter K. And the K represents the resistivity of the conducting material, or the conductor's material. Now, how do we determine this? Well, I'm going to tell you right now, before I get you confused, there are 2 values that you can always use, whether you're dealing with copper or you're dealing with aluminum, that you're going to plug into your formula when you're dealing with copper or aluminum. Okay, so you want to write these down. When you're dealing with copper, the K value is 12.9. Now, I'm going to show you how we solve this to find out what the real actual K value is. I mean, the actual, not an approximate, but the actual. Okay? Now, when you're dealing with an aluminum equation on an exam or in real life, the aluminum K value of approximate K is 21.2. So remember, 12.9, 21.2, 12.9, 21.2, depending on whether you're dealing with copper or aluminum. Now, how do I find this value, the real accurate value of this? Okay, let's take a 6 AWG copper conductor, because it just is a good one to use. And we're going to use that, and we're going to say we need to solve for K. How do we do this? Well, first thing we do is we need to find out what the circular mil is for that 6 AWG. Well, where are we going to go? Chapter 9, Table 8, we look down and we see that the circular mil of a 6-gauge copper is 26,240. That's what the area is in circular mils. Now, the next thing we need to know is, what is our ohms of that 6 AWG per foot? Now, we know this table on Chapter 9, Table 8 gives us per 1,000 feet, but I need to find it per foot. So remember what we said earlier? It's pretty simple to do this. We just need to take the equation and work it out. So we take what is it per 1,000 feet? In our case, we're using uncoated copper. That's the standard bare copper. And we'll see that the 6 is 0.491. So we take the 0.491, we simply divide it by 1,000, and that equals 0.000491. That is the value per foot in ohms. So you just multiply the two. 26,240. You multiply it by 0.000491, and that equals 12.88384. Now, since it's 12.8, you know that's why we get the approximate value of 12.9. It's because they rounded up to 12.9. But the most accurate you can be is 12.88384. And if you use that in your equation versus the 12.9, the decimal that it changes is so far out that it doesn't make a hill of beans. Okay? So that's why it's much easier to use the 12.9. Now, again, it doesn't matter which conductor size it is. If you wanted to solve for the absolute K versus the approximate K, then you do the same thing. You simply take the circular mils and you multiply it by the actual ohms per foot. And now you know how to do that by taking the actual value that's in Chapter 9, Table 8, and taking that value and dividing it by 1,000. That is your per foot value. It also happens to be the R value that we're going to solve for in a little bit later. And so you take that value, and that is going to, and you multiply the two, and that's going to give you your absolute K. But again, for an exam, you really only need to know the approximate K. So that's why you remember 12.9 for copper, 21.2 for aluminum. Okay? So I just gave you a lot of information to maybe help you be a little smarter than the next guy, but that's how you solve that. Okay? Okay, so the next letter you're going to see in your formulas that we talk about is L, and that represents the length of your circuit, okay, from the source to the load. Now, this is one way only, from the source to the load, one way. That's it, okay? You're not accounting for down and back, okay? That's already done with the 2 that's in the math, in the formula, okay? You don't need to do it. Now, what could you do? Could I get rid of the 2 and just take the length one way and do it times 2 and put that value to? I guess you could, but why would you want to make it complicated? Remember, the formula is simple. And when we look at the formulas, 2 represents single phase down and back, okay? That's what it represents. All you have to do in the equation when you see an L is put the length in one way, okay? If it's 150 feet away, you put 150 feet down. That's it, okay? Don't make it overly complicated. The reason is so some people forget, and they might drop the 2 and they forget to take the length and still do it one way, and then they're going to get it wrong, because in that case you're going to have to assume both ways, okay, when it comes to the distance. So it's easier to leave the 2 in there and just think of it as one way, okay? Don't make it any more confusing than it needs to be. All right, the next letter you're going to see in the formula is I. I represents current, and it's the actual current used, okay, by the load. You're not going to factor in 125%, even if it's a motor, or if it's even a continuous load to whatever it is out there. You're not going to do that. You're simply factoring in, okay, the actual load itself. That's what we're factoring in, okay? So ignore the 125% for a motor, or even if it is a continuous load. Only deal with the actual load. Now, where could that come into play? So say we're looking at a motor, and we're sizing this motor, whatever the horsepower may be. We're going to go to 430.248. We're going to look down the list, and we're going to find what the FLC is, full load current of a motor, in amperes. That is the actual load of that motor. That's what you plug in here. You're not going to figure in 125%. You're not going to assume for continuous load. You're simply going to take the actual load when you're doing a voltage drop calculation. Okay? The last one we're going to look at, we actually got one more, circular mill. We already know what circular mill is. You're pulling it from Chapter 9, Table 8. So anywhere in the equation that says C mill, you know what you're getting. You're going to the area column of Chapter 9, Table 8. And you're pulling it. Obviously, if it's 250 kc mil and larger, then you already know what the C mil is. Now, this is an example where you wouldn't put 250 here. You got to break it all the way down. So 250 would be 250,000. Okay, that's what the K is in 250 kc mil. Okay, so you have to break it out, okay, into the value. All right. All right, so that's how we're dealing with that. So that's your circular mill whenever the equation asks for that. And then lastly is the R. And believe it or not, we've already figured out what R is. And R is the conductor's resistance for 1 foot. So depending on the formula, if you see R in there, it's really trying to find what the resistance is for that 1 foot. And so how did we do that? Well, we did it already. We took the actual value of a 6 AWG per 1,000 feet from Chapter 9, Table 8. And to be honest with you, even if I was using Chapter 9, Table 9 per 1,000 feet, we do the same thing. It doesn't matter whichever one you're using. Again, if we're taking an exam, most often than not, it's going to be on DC. So we're going to be in Chapter 9, Table 8. But either way, it wouldn't really matter. And so it's per foot. So we take the 0.491, which is per 1,000 feet, divided by 1,000, and that's going to give us our R value, or per foot value. Okay, so now we know how to do that. Let's kind of look at the various formulas that we can use to solve different things. Because depending on what the question on an exam or in the real world, depending on what they give you, you have multitude of formulas. I can solve for voltage drop. I can solve for circular mill. I can solve for the R, which is conductor resistance per foot. I can solve for the current, the maximum current in amperes. I can solve using Ohm's law or this formula I'm going to give you. I can do a lot of things. I can determine the length, the maximum length that I can have of a circuit based on any given thing that's presented to me using all these formulas. Okay, there's about 8 different formulas that we typically use. Okay, but you might not need them all, but we're going to go over them so that you kind of understand them. And again, we're doing single phase right now. Okay, there's a few more formulas when you're doing 3-phase, but we're going to talk single phase right now. So the very first one is used to find the voltage drop in a single phase circuit. Okay, so what we're solving for is the actual voltage of drop. Okay, so the formula is, okay, so what are we solving for? We're solving for VD. That's what we're solving for. How do we solve for it? Well, let's say we know the conductor size. Let's go on and do that. So it would be the formula, and if you got your pencil and paper, this is where you want to pause, get ready, and we're going to write these down. So formula number 1, we're solving for VD, and that is 2, that's the number 2, times K, and And we said that K, if it's copper, is 12.9. If it's aluminum, it's 21.2. Times whatever the length is in your equation, times, and that's an L, times I. And I is the actual current. Okay? So that's the top. Then you draw a line under that, and underneath it, it's C mil. So that's the circular mils of the conductor you're selecting. In this case, say it was a 6, that would be 26,240. So it's 2 times K, which is 12.9 of copper, times L, then I'll say 150 feet, one way, whatever it was, times I, it's a 6, so let's say it's 65 amps, and you divide that value by the circular mil of that 6, which was 26,240. And that's going to give you your voltage drop, okay? So if we did that, let's base this on 150 feet, and let's kind of work this one out. All right, so let's go on and do it. That way we can see how it works. So in our case, let's say that we got to find a voltage drop. So let's say we've got 150 feet. We're using 6, and it's based on 310-15B16. Let's just take the load at maximum, just for giggles. It's 65 amps is what the load is. Of course, that's what the conductor can handle, but we're just using it to solve equation here. That's all. All right, so we go 2 times 12.9, because we're going to do copper, times 150, times 65 amps. That's whatever that was our load was. That results in 251,550. So that's the top part of the equation. Now we're going to divide that by the circular mil of the conductor in question, which is a 6. So in that case, it's divided by 26,240, and that's going to equal 9.58. That is our voltage drop. Okay. Now, if we want to find out what the percentage of that is, convert that to 60, we take this 9.58 and we divide it by 120 if it's a 120 volt load, and that equals 0.079, which you move the decimal over 2 spaces to the right, then it's 7.9% voltage drop, which again exceeds the 5% overall, or it definitely exceeds 3%, depending on whether or not we're dealing with a branch or feeder, whatever. That's how you come up with the voltage drop, and that's how you can convert it to an actual percentage, okay? Using that formula. That's as simple as that, all right? And so we'll stick with that motif as we move through. We'll stick with the 6 gauge and 150 feet, and we'll work that way out, okay? All right, so the next formula, or the next thing we're dealing with is the next formula. And this is where we're trying to determine voltage drop. And here's another formula when you're finding the voltage drop in the circuit. And this method actually uses Ohm's law. And it does use the resistance. So here you see the R is included in this one. And you use that instead of the K. Okay? And you don't use the circular mil here. So we're simply using the resistance value. So how do we solve this one? So here's the formula. VD, which is our voltage value, it equals, okay, so here's the formula. 2 times R times L times I. Okay, remembering that 2 times R is the resistance per foot, and you saw how we calculated that, times the length, which is 150 feet, times the ampacity, or the current, the actual current of the load, okay? So in this case, 2 times, we've already done this, 0.000491 times 150 feet times 65 amps, we'll just use it and keep everything consistent. That results in a 9.57 as your voltage drop. And again, then you can take that and divide that by 120 if it's a 120, and that's going to tell you that's still 7.9. The decimals really aren't going to matter in this case. It's still 7.9% voltage drop. Okay? Not good, but that's what we've got. And again, you do the same thing, and if you wanted to do it and find out what it is at 240, then you could. You just simply take those values and you will divide it by 240 instead of 120. Same concept. All right, so that's how you find it. You see that works out. So the next one we're going to look at is, what about length? So what if we want to find a formula to do the maximum length? Well, because we're using 2 in the equation, this is going to deal with the formula. So we're only going to have a length of one way still figured in here as far as the length. But we're able to figure it out because we do have a 2 in here. So how do we solve this one? So we want to find the maximum length, okay? And this length is one way. So to find for L, we have another equation here. So it's circular mils times VD. Now remember, VD, you don't put 3% in there or 5% in there. You're putting the actual voltage being dropped in there. So it's circular mil in our case, it'd be a 6 gauge. So we said it's 26,240 circular mil times the voltage drop. If it's a 120, then we do it at 3.6. If it's 240, we're doing it at 7.2, which would equate to that value for the 3%. And then, of course, you divide that or put a line under it, and it's 2 times K times I. So let's kind of solve this out and find our length, our maximum length this way. All right, so let's take what we've got. Now, let's just assume here that we're dealing at the 120. So let's do some length here. So circular mil, we'll take let's get your calculator out. Take 26,240, and we're going to multiply that by the voltage drop, the actual voltage value. In this case, if it's a 120 volt, we're going to say, since we're working with 3%, we don't want to exceed that in our example here. Then we would plug in what the actual voltage drop is. And we determined what that was and how we calculated that. We did that earlier. So it's 3.6 volts. Okay? That is what? How did we determine that? Again, we calculated it earlier by saying, how do we break it down? It is simply 120 volts times 3%. That's how you got the actual voltage value. And if it was 240, again, it's 240 times 3%. If it was 5%, you're doing it overall, you do it the same way. But here we're sticking with branches. We're going to do the 3% and factor it out. Okay, so it's circular mils, 26,240 times 3.6 equals 94,464. So you write that down. So that's the top part of the equation. Now you have a line, and underneath it you got to go 2 times K times I. Okay, so 2 times the K, which copper, 12.9, times I. We said arbitrarily our value was 65 amp of the load. That's what it was. Then that's 1,677. So you take the 94,464, you divide it by 1,677, and that gives you 56.32. So really 56 feet is the maximum length you can go and not exceed the 3% voltage drop. So that's how you calculate the length. Okay? All right, so if it was 240 volt, then you would substitute the voltage drop value of 7.2, where we put the 3.6 in there, do the same thing. So that's your maximum length, one way that we can go. Okay? How do we do another length? So we have another one that we can do, depending on what your question on the exam asks you about. If we want to do one, we're just solving with Ohm's law. We can come up with the same type of concept. Now that formula for that length is that it's the VD divided by 2 times R times I. So in this one, we got a percentage of voltage drop that we know. We're converting that to an actual voltage value. In this case, if it's 120, it's 3.6. If it's 240, it's 7.2. And then the resistance, or the R in the bottom part of the equation, because the other ones are easy. 2 times R times I. We know I was 65. That's what our load was. How do we solve for the R? Well, we've done it multiple times here. You take the resistance of that conductor that's in choice that we choose, which is a 6 gauge. We take its actual ohms per 1,000 feet, which is in Chapter 9, Table 8. And we take the 0.491 divided by 1,000, and that's the per foot value, 0.000491. So how do we do this math? We're going to do it, if it's a 120 volt, we go 3.6, put a line, divided by 2 times R, which R is 0.000491, times I, and I in our case is the current of the actual load, which we said arbitrarily was 65 amps. So we work this formula out, and that can give us a length as well. So let's do that. All right, so really the beauty of this is that you get a lot of ways to do it based on what the exam question will ask you. And you just need to know that the different formulas on how to do it. And so studying them, looking at them, again, if you're in a state that allows you to write in the front of your code book and make notations, then this is going to be extremely beneficial to you. So let's do this. So the voltage drop that we're trying to achieve, 3%, and we did it, and we did 120 times 3%, which resulted in 3.6. That is our voltage drop that equates to 3%. So we do 3.6, and that's divided by 2 times R times I. Well, 2 times R, which is the R was the 0.000491, which again was taking the value of 1,000, the resistance in ohms for 1,000 feet of 6 gauge based on Chapter 9, Table 8, which was 0.491 divided by 1,000. That's how we got the 0.000491, times I, which is the 65 amps. That's going to result in a 0.06383. Okay, so you simply take the 3.6 and you divide it in the 0.06383. And that's going to be 56.39. So 56 feet is your maximum length. Okay, so either way, I'm able to do it. The other one I solved by the resistance, which equals to whatever it was for the 6 gauge, or if we knew what the circular mills, we could use the circular mills to solve it. So if you get an exam question that doesn't give you the circular mills, but gives you a resistance value, then you can solve it. Okay, so just kind of giving you ways to be able to solve for the maximum length. Okay. All right, so the next equation is, what if we want to solve what circular mil of conductor that we would need based on the variables of voltage drop and the length and everything? So maybe we can solve it this way to find out what size conductor we need to pick from Chapter 9, Table 8 in order to achieve that we don't exceed the 3%. So here's another formula, and we're solving for circular mil now. And the formula is this: 2 times K times L times I. You see a pattern here? It's simply substituting values to be able to solve for them. And you're dividing that by the actual voltage drop. Okay? So let's work this one out, and we'll see what we come up with for the circular mil. Okay, this one's going to get quite interesting, because watch what I'm going to do here for you. I'm going to help you out, and we're going to learn something here. So if earlier we just chose a 6, and we know that one was way over 3%, right? That was like 7 something or 7.9%, you know? So let's kind of figure out what we would really need to comply with the 3% value, if that's what we were shooting for this 150 feet. What size conductor would we really need to achieve this for voltage drop? Let's do that, because we haven't done that yet. So earlier, we're just picking a 6, and of course, if we were trying to achieve the voltage drop parameters, we know that we couldn't use 6. So we keep jumping up in size and doing a bunch of math to try to find the answer of what conductor we need. Using this formula, we can immediately find the conductor we need. So let's show you how to do it. So the first thing to solve for the circular mil that's necessary, or really the size conductors necessary in order to achieve this 3%, we go 2 times K, which in this case is 12.9, times the length, which is 150 feet in all of our examples so far, times 65. That was I, the current. Okay, so it's 2 times K times L times I. And that's going to result in 251,550. So you write that down. Now, draw a line, and under that is the actual voltage drop that we're trying to achieve. So in this case, we knew that the VD was 3.6 if it's 120 volts. If it's 240, then we'd use 7.2. Remember, VD, we want the actual voltage that's being dropped in the circuit, or the maximum allowed to be dropped. Okay? So, in this case, we take 251, 550, and we're going to divide that by 3.6, because we'll just do a 120 volt circuit here. And that equals 69,875. Now, that is actually the circular mil. So we have to go to Chapter 9, Table 8, and we go to that third column from the left area, and we got to go down these circular mils. Now, we see a 2 gauge is good for 66,360. That's not going to work. Not going to work. So we have to go to what? Down to a 1. So we go to a 1, and 1 is good for 83,690. Okay, we're good to go. Now, we could play with the values and see what put us at 66,360, but since 3% was our maximum and we worked it out right here, we know that it has to at least be 69,875 circular mils to be able to be okay. So here we're going to choose a 1 gauge in order to make sure we fall within that parameter. Okay? All right. So how we can work this out and show that we were so wrong with the other one? Let's do this. Let's calculate what it would be for that 6. And we already know what the voltage drop is, 7.9%. Okay? But we needed to know what the actual voltage drop, and that was 9.58 volts. So let's do this. Let's do the 2 times K, which is 12.9, times the length, 150, times 65, and again it's 251,550. Now, for the voltage drop, in order to kind of simulate what we did with the 6, which we know isn't what we want, but let's go on and do it. So it was 9.58. I believe that was the value that we had. So let's go on and do this. So we've got 251,550, and we're going to divide that point 9.58 that equals 26,256. So if you go back and look here, then you'll see that it actually was trying to put you in the 6, which was 26,240. Okay, and this one's 26,257. So why did it say that difference a little bit? Probably because I didn't work out the total equation out there. So if you're arbitrarily picking a value like 6 gauge, and you've got to go through all these in order to try to get you all the way down to the 3%. Okay? So here, I can literally do the equation and find the exact circular mil that I need in order to be able to do the calculation. Okay? That's the real proper approach to picking the conductor. Okay? And there's always some nuances in decimals and drops and things like that you have to work out. But in our case here, you notice that even when we ended up in 1 gauge, it was slightly more circular mil than necessary to be able to do the equation. Okay, so I just wanted to show you all the ways to be able to equate it out. And so in reality, I think what really happened was you needed to use all of the factors. So I just redid it, and it was actually 9.586. So if we redid that calculation, we did 2 times 12.9 times 150 times 65, and we did that, and that was 251,550. So it's 251,550 divided by actually the 6 gauge, which we calculated earlier, which is 9.586. That equals 24,241. Okay, so then when you look at the 6 gauge here, you see it's 26,240. So I think it was close enough. It was still 3%, but it might have been slightly over. But we arbitrarily picked a 6 to do it. So I didn't use all the decimals out. Okay, so you see, if you want to find the most accurate circular mil to be the at least size you need to meet the voltage drop, which is a recommendation only, remember that, except for when you're doing fire pumps. And if that's the case, you're going to want to find the exact circular mil that's necessary, and that's when you'd use this formula. But I think you see how they work back and forth. They get you right in that area of 3% voltage drop and whether or not you're dealing with it. Okay, so the next formula we want to look at is how we can find the Ohm's law to find the conductor size, okay, which is another way to do this to find it. So how do we do this one? And where you're going to use R to do this. So the results in the minimum conductor resistance for 1 foot. This keeps the voltage drop below the VD used in the formula. Okay, so below the voltage drop of 3%. So let's kind of figure this one out a little bit. Now the formula here, R equals VD divided by 2 times L times I. Again, we know by now the length is 150, the I is 65 amps. The voltage drop, in our case, we're going to now kind of keep ourselves in the realm of what would be 3%. So that's 3.6 for a 120 circuit or 7.2 for a 240. Since we're doing this at 120, just to keep it simple, let's do the formula here. So voltage drop, in our case, would be, so when we're doing this one, let's do this one here. So voltage drop, 3.6, because that's for the 3% for the 120. And we're dividing that by 2 times 150 times 65, okay, to come up with a math. So I think it's easier if you work both of the equations. So we know what the VD is, 3.6. So let's do 2 times 150 times 65. That's 19,500. So take the 3.6, divide it into 19,500, and that equals 0.000184. Okay, so that is the resistance per foot. So if you go back to Chapter 9, Table 8, and we're going to try to see why we would select a 1 gauge like we did earlier when we did circular mil. And if you go over and look at it, you'll notice that under the uncoated copper per 1,000 feet, the resistance is 0.154. Now notice that the 2 is 0.198. So this is per 1,000 feet. So in our equation, we have it per foot. So what we would do is we actually, and I find it the easiest way, is to write down 0.000184 down. Now, you could probably look at this and realize you add 3 zeros to this or you take 3 zeros away from it. But me, I look at the resistance up here and I convert it again. So I take that 0.194, okay, and I'm going to do this now divided by 1,000. 194 divided by 1,000 equals 0.00019. Well, now I have to stay at 0.0018, so that's not going to work for me. So when I go down to the number 1, which we determined was earlier, might have been a little larger than necessary, but it did make sure that we complied with the 3%. That one's going to be 0.000154, and that is better than the 0.00184. So it falls in between there, so that's why we're going to result in going to size 1. So that one's a little more complicated to do that because you have a little more of a math. I would probably use the circular mill formula that we just did, but that is simply another formula that you can use. Okay? Now let's go on to another formula. Let's solve for I. Okay? How do we solve for the maximum amps that we can use? And then we're going to get away from our values and try to solve based on the conductors we're choosing here, because I was just arbitrarily throwing you a 6 gauge before so we could use that for math. Now we're getting to find out actually what the ampere rating is based on our parameters here, okay? Okay, so what you're going to find is that even though I used that 6 earlier, that is not going to work. But let's go on and do it anyway. So let's find out what a 6 gauge, what is the maximum amps at 3% voltage drop, what is the maximum amps that we could have in order to still achieve it? Or what amps can we determine the current? So let's do it. So circular mill times the voltage drop. In our case, let's just say we're going to use that 6 and find out what the real, because we were using it earlier, and we found out that we had to jump all the way up to a 1 gauge, but we just want to play with this 6 again. Find out what is the actual current that could travel on this based on the voltage drop. All right, so circular mill, 26,240 times the voltage drop, which in our case, 120 volts is the source, and we did the math to determine that. We did a calculation, and that was to actually take and solve for what our voltage was. Okay, and we did that earlier, but again, just in case you forgot, it's 120 times 3%, that equals 3.6, or if it's 240, you're dealing with 240 times 3%, that's 7.2, so that's what we got our VD. So let's do this. So 26,240 times 3.6. And so I'm going to do it with you. We can do the math. So 26,240 times 3.6, and that's 94,464. So you write that down. That's the top portion of it. Okay. Now you draw a line, and now you're going to solve the bottom portion. So the bottom portion says 2 times K, which is 12.9 if we're dealing with copper, 21.2 if you're aluminum. Times the length. In this case, it was 150 feet. Okay, so that equals 3,870. So now it's a simple aspect of taking the top value, which was the 94,464, and dividing it into the 30,870. So let me do that. 94,464 divided into 3,870. That equals 24.4 amps. So that 6 gauge, based on this length, okay, the amount of amps that we can have, or the maximum current in amperes, is 24.4 amperes. And that's the maximum current. Okay? So obviously, if we did this equation with the number 1, that's going to get us closer to what that 65 was. So let's do that and just see what we're dealing with. Just to double check ourselves. That's how we're using all these formulas, because we use 65 amps in all of our other equations. All right, so the circular mill for number 1 is 83,690 times 3.6. Again, that was our actual voltage that's dropped based on our length that we're dealing with. Or we don't want to exceed 3%, and that's how we came up with that. Again, 120. If you don't remember how I did that it's 120 times 3%, and that's how we got the 3.6. All right, so circular mill times, which is 83,690 times 3.6, is 301,284. And then the bottom equation is 2 times K, 12.9, times 150 feet, which is 3,870. So you divide the top into the bottom, so that's 301,284 divided by 3,870, and that gives me 77.85 amperes. So slightly more than 65 amps that we worked with, but that's perfectly okay. So since we had to have at least the 65 amps, that's what our load was, okay, so that's kind of how we worked that out. All right. Now, there is another way to solve this using Ohm's law. And so we're going to solve for I using Ohm's law. Now, this formula is voltage drop, and again, we're going to use for 120. If it was 240, use 7.2. For 120, we're using 3.6. So it's 3.6 divided by, and you draw a line, it is 2 times R times L. Okay, so the R is the resistance per foot. Okay, so in our case, we jumped up to 1, so we got to do that little equation, right, in order to determine what our values are. So let's do that. So let's determine 1. So in a 1, it was 0.154. So we took that 0.154. All right, you're all following along with me. We've done this many times so far. And we're dividing it by 1,000. And that equals 0.000154. Okay. If you're used to seeing all this and you think, ooh, it's 1,000, take the 3 zeros from 1,000 and add it to this value. I have some people that do that as a shortcut, and that's okay. It's just simply add 3 values to what you see right here. It's fine, but I always like to work it out just to be sure. Okay. So that's what my R value is. So in this calculation, I'm going to take the 3.6. And I'm going to write 3.6, and I'm going to write that down as my first value. That's my volts. Now I'm going to do 2 times, and I've already done this, 0.000154 times 150 feet, and that equals 0.0462. So now I take my 3.6, and I'm going to divide it by 0.0462. Okay, and you're going to see that comes up to 77.9 amperes. So it works out either way, but this allows you to be able to solve it. Whether or not you're given circular mills or not, you can choose if it's giving you resistance for a specific value per 1,000 feet, then you know how to break it down into per feet, and that's what you're going to use in this formula because that's what R represents. Okay, so again, all of that stuff. There's 8 different formulas here. Hopefully you understand all of those and we've made it easy. Now, let's move on to 3-phase. Now, when dealing with 3-phase, the formulas are the same. K means the same, L means the same, I means the same, R means the same. There is no difference here. Just remember, when you're multiplying the factor for 3-phase, you're going to use 1.732. That is the square root of 3. It represents the conductor's length in a 3-phase circuit. The only difference between a single-phase and a 3-phase formula is that 1.732 replaces the 2. Okay? So once you've learned all these formulas here in single-phase, then you can get away with remembering that I'm simply replacing the formulas with 1.732. All of the same formulas generally work out, okay, and they're all generally the same, okay? But we're going to go through them because I want you to see how this feels. All right, now, here's how we find the formula in the 3-phase. Now, these formulas, to find the maximum length and distance, okay, we have a formula for that, and again, it's one way, and we're going to use 1.732 in place of 2. Okay, so you have a bunch of different variations that you can use as well. But I'm going to give you the basic ones, which again are no different than what you just did. The only difference is where it says 2, we're substituting 1.732. Okay, so instead of doing examples like I did before, we'll just kind of go over them here so you can get an understanding. So if I want to find the voltage drop again, and we want to find that in an actual voltage value, in a 3-phase, we do 1.732 times the K, doesn't change, 12.9 for copper, 21.2 for aluminum. L is the length, one way, times I, which is the current, the actual current. So nothing changes. You divide that by circular mill. Okay? Nothing changes. Now, if you want to find out what that circular mill is, before you even try to do this, then you say, well, what conductor I need to have to meet that 3%? What's the maximum size? Okay? All right, so we can do 1.732 times K times L times I divided by voltage drop value, which is the 3.6 volts. And if you do that, that's going to result in your circular mill. Then you just simply go to Chapter 9, Table 8, and find the conductor that can cover that circular mill, knowing that it might push you to the next size, because you at least need to have that size there. And since not every circular mill is going to be represented here, you do have to run to the next one. Okay. If you just want to find voltage drop, again, the same as before, one of the values that you can do is 1.732 times R, which is resistance per foot, and we've already explained how you do that, times the length times the current, which is I, and that is the actual current. Okay, so rather than get overly redundant, the same formulas apply for single phase that apply for voltage drop in three phase. Don't get it confused. Don't get overly concerned. Now, I'm going to give you some alternate ways to do this. Okay, now don't stress on me. Don't get all stressed out. But I'm going to show you some alternate methods to do this. Okay, all right. So one of the methods here is to look at this formula. And I really shudder if I'm going to really stress anybody out here in doing this, but I'm going to do it anyway. So we want to find the voltage drop value, and the application is three phase. How do we do that? All right, so this formula is no different, and this is to be able to use the single phase formula. And in case you don't want to get overly complicated, and in case you forget about the 1.732, and you just want to remember the formula with the 2 in it for single phase, here's a little trick. You can go 2 times K times L times I times 0.866. And then you draw a line, and then underneath it, you divide that by the circular mil of whatever conductor you're dealing with. Like, let's say if it was our 6 gauge we were talking about. So that's going to be able to give you the voltage drop, which is going to be a little different than the value that we got for single phase. All right, so in this case, it would be, and let's go and do it. Let's do it so you can see. Now I want to do both so you can see how this works. So if it was single phase, I want to find what the voltage drop would be for a 6 gauge in single phase versus 3 phase. Kind of let you see how this works. And this is an alternate formula now, okay? You could just use the 1.732 times K times L times I divided by circular mil. But what if your mind is locked in on the single phase where you're adding that 2 in there and you forget about the 1.732? This method allows you to remember, well, if it's 3 phase, I just add the 0.866 to my multiplication. Okay, so let me kind of show you how this works. So if we were dealing with single phase, it'd be 2 times 12.9, we're doing copper unless expressed otherwise, 150 feet times 65, which is the amps, that's I, equals 251,550, and we divide that by 26,240, which is what the 6 gauge was, just for whatever giggles it was. All right, so that gives us 9.58, okay, is the voltage drop. Okay, so if I want to do the same equation over here for the 3 phase, and I could use the regular method, which is 1.732 times 12.9 times L, which is 150 feet, that's the length, times 65, we've been using that all day, so we'll use that as amps, and that is 217,842.3, and then we can divide that by 26,240, which is the 6 gauge circular mils, and that is 8.30, and that is our voltage drop. Okay, well, what about an alternate formula? If you, just in case you want it. Well, again, say your mind is locked in on that, putting in that number 2. For some reason, you're stuck and you can't remember that 3 phase is 1.732. Although I don't know why you would not remember that, because I'm going to ask you to remember something else. But anyway, I want to give you alternate methods. So if I still do that same thing, I'll do 2 times 12.9 copper times the length, 150 feet, that's the L, times I, which was 65. Now, there's one more thing to add. Now do it multiply times 0.866. So add, once you get to the 65, do another times, and then you're going to do 0.866. And that equals 217,842.3, the same as you got before. And then you simply divide that by the circular mil, 26,240. And that still gives you 8.30. So that's just another way to do it. It's easier for me to tell you to remember that to single phase, add the 2. If it's 3 phase, do the 1.732, and then you'll never have to worry about it. But I figured I'd give you an alternate method to do that. Okay? Now, there is also an alternate method for the length. And it's the same thing. Use the same formula you did in your single phase, but then you add on the bottom line, you just simply multiply it again by 0.866. So it would be circular mil, in this case 26240 for a 6 gauge, times 3.6, that's our voltage drop for 120. Okay, and that equals 94,464. We've done that before. We did that with the single phase. That didn't change. Now, you divide that by the bottom part, and that is 2 times K, which is 12.9, times 65, that was I, the amps, and then you do one more step, you multiply that by 0.866, and that equals, that value is 1,452. Okay, so then you're going to take the top and you multiply it into the divide it into the bottom. Okay. All right. So circular mil. Let's go on and do it. 26,240 times 3.6. That goes 94,464 as we had before. Again, I just want to make sure we're all on the same page. Then you take 2 at the bottom part. You take 2 times 12.9 times 65 times 0.866, and that is 1,452.28. So then you just divide the top into the bottom, so it's 94,964 divided into 1,452.28, and that is 65.3. Again, 65 feet is the maximum length. Okay, same as what we got before. So those are some alternate methods. I kind of was redundant on them. Just remember, you still have the 8 formulas that you would use, whether it's single phase or 3-phase. The only difference is you're substituting 1.732 if it's a 3-phase, and you're using 2 if it's a single phase. That's the main difference that you're needing to focus on. Okay? All right. So that kind of gives us the overall concept of what we're working with. So hopefully you got a little bit of a better understanding of how it works and what we're dealing with and how you apply all these things when it comes to the dealing with voltage drop. Again, remember, other than fire pumps and sensitive electronic equipment, where it's mandatory to consider a voltage drop, everywhere else in the code, it's just really good information. It's informational note. It's a recommendation. I'm telling you, it's great that you do consider it because we want everything to operate efficiently. And if it's not going to operate efficiently, then it can prematurely fail or potentially cause a fire. So it's important to understand voltage drop. Not everybody takes it into consideration. There's a lot of free calculators out there that'll do it for you. But again, now that you know how to do the formula, now that you know how to do everything, then it should be pretty simple for you to do that. So hopefully you got something out of today's podcast. Again, voltage drop is an interesting topic. And while I wish it was mandatory in NEC, it is only dealing with fire pumps and sensitive electronic equipment, as we talked about earlier. But it's just really good, especially for an exam. You need to know all these formulas. So at the end of the day, stop and pause and go back and listen to the formulas again. I talk you through them. They should help you understand how to pass an exam when it has voltage drop calculations on it. And it ought to help you in the real world. All right, folks, till next time, stay safe, God bless, and thanks for listening to our podcast.
Every day, the future's getting closer. Every day, the future's looking bright. Every day is another beginning.